So somebody else keep an eye on folks coming in to let them in if they can, and I'll do an introduction. So hi, I'm Paula King, and I'm a member of Seattle Friends of Fission. We keep saying we need to be something wider than just Seattle Friends of Fission, but we haven't quite made that change yet. But we do talk to folks all around. It seems to get a little larger, which is good. So we're going to have Dr. Jim Conca talk to us about the future needs of energy in Washington and how nuclear energy can help us overcome the effects of climate change. Seattle Friends of Fission is a grassroots organization. We've been bringing speakers to the area, to different brew pubs, Ada's bookstore, all sorts of different sites for about 6 years now, talking about having different folks, Jim and other experts in different aspects of the field, talk about climate change and nuclear power and try to answer people's questions and myths and misinformation and lack of information, which is certainly someplace I started from. So Jim, Dr. Conca, is a scientist in earth and environmental sciences, is specializing in geologic disposal of nuclear waste. He spent many years working on that, I think around 30 plus.
Yeah.
And he's worked on energy-related research, worked for NASA, I think even before all that, and issues of exploration in space. He's worked with the DOE, EPA, and state environmental organizations, and lots more. So I'm going to let Jim start, and then after he's done, we'll have time for lots of conversation, questions, and so forth. So enjoy.
Good. Great, thank you. Let me...
You can start sharing over top of mine.
Yeah, let's do that. All right, can everyone see that? You got that?
Yes.
Oh, good. So anyway, so I appreciate this. Some of the names I recognize. You've probably seen parts of this in different talks I give, but yeah, this today is really focused on Washington State. But we'll talk about some generic stuff as well. And I want to start out talking about Washington State. So Paula sent this around. This is kind of what to expect in the mid 2030s if we continue the way we are now, which we will, of course. That's not very far away. And the overall global warming is 1.5 degrees C. So in Washington State, we're a little ameliorated by the Pacific marine effect on climate, which is good. Especially the people on the west side, on the other side of the mountain Cascades. I'm not quite over here on the eastern side. We're not quite as mitigated, so it gets a lot worse here. But you can expect, a lot more hot days, and of course, related to that is heat-related illness and deaths. We've seen that the last heat wave we had here last year really hurt Seattle, because Seattle only about 50% of the residences in Seattle, in fact, on the west side totally, have air conditioning. Well, and I didn't know that until this heat wave. And so it was very stressful. People died. And so, it's really, really tough. The biggest problem with global warming in Washington State is that we will not get the snowpack we're used to. And that's really important for rivers like the Yakima River, that grows an awful lot of the crops that feed both Washington State and the world. The Skagit River, things like that. So, the rivers that depend on snowpack in the mountains of the Cascades are going to be really hurt. Now, fortunately, the Columbia River is almost unaffected by global warming. So its flow will hardly reduce. The temperature of the flow will hardly reduce, but all the other rivers in Washington State will be heavily affected. Again, because it's going to be warmer, because you don't store the snowpack, more of the snow and rain will flood during the winter time, which is unusual and we're not used to that. And so that has a lot of negative effects, especially flooding, and the temperature of the rivers themselves. Lower summer stream flow, which also affects the temperatures of the runoff, and there will be much less stream flow because of the less snowpack. Sea level rise in Washington State isn't so bad. I mean, it's a little bit, but it's not so bad because we don't have a lot of land area at sea level. And there's some places, around the Sound, there's some places on the other side of the Olympic Peninsula, but in general, we have pretty high elevations close to the ocean, so we won't have that much problem. Unlike places like India, Bangladesh, those the islands of the Pacific, they're going to be really hard hit. So I want to go over climate change in general. So this is a very busy slide. So this is climate change over the last 500 million years, 542 million years to be exact. That's when fossils first appeared. So we have good data after fossils appeared. To fit 500 million years on one graph, I had to compress it. So this is thousands of years over here on the right, then hundreds of thousands of years, millions of years, tens of millions, and hundreds of millions. Okay. So what should jump out at you right away is that the Earth in general has been very much warmer than it is today. Okay, we are in an extreme cold spell for planet Earth over the last 4 billion years. So much so that in the last 10 million years, it's been very cold. In the last 2 million years, we've had glaciation. Now, glaciation is a rare event on Earth because you need to have the fortuitous assembly of astronomical positions as well as plate tectonics. You have to have land masses at the poles, at or near the poles. So that, of course, has happened after Pangaea and Gondwana land split up. So we have, the Antarctic continent at the South Pole. We have a lot of the northern continents that are very close to the North Pole. So we have a lot of area in order to accumulate ice. So the ice sheet in Antarctica is 3 miles thick, 3 miles thick, and in the north it's a couple miles. So this is an important issue. So we've been very cold, and so a lot of people say, well, gee, if it's been so warm in the past, then what's the big deal? Life evolved very nicely and under such warm conditions, and who cares? And CO2 has been a lot higher. I should mention this is the temperature difference from the zero, which is the 1850 baseline, the year 1850 CO2 concentration and temperature of the atmosphere. So hey, who cares, right? It's been warmer. Well, it turns out it has nothing to do with the absolute temperature or the absolute concentration of CO2. It has to do with the rate of change. Okay, biota on Earth do not like change. I don't like change. My cats don't like change. Okay, if you change too quickly, you die. It's called extinction. No big deal. It happens all the time, unless you're the one being extincted. So again, this has nothing to do with the absolute temperature. It's just that if you look at the last 150 years, we are coming out of this cold spell rather fast. And that's the problem. Things cannot adapt when you actually change it so fast. And because of the compression of the time scale here, this is only 150 years. Well, this is like, 100 million years. So if you looked at the present rate of change and compressed it to the same as these older scales, it would be a vertical line. I mean, it would just be a vertical line. We've come up so fast, so quickly, that the biota generally does not have time to deal with this. Now, when you look at modeling, I hate modeling, excuse me for putting up models, but when you look at the climate change models, there are two end members, okay? And you look at this within the literature, and you'll see A2 and B1. So A2 model is nothing happens. I mean, business as usual, okay? We are presently over 80% fossil fuel for primary energy. And, so this model says, okay, we're still going to be 80% fossil fuel by the year 2100. And this is what happens. It gets quite hot. There's some slop in this, but so you think of this is an average hot. Now, B1 is significant reductions, meaning pretty much everything we think we can do. If everyone starts right now in full tilt and all countries are on board, this is what happens B1. It's not that great. I mean, it's not fantastic or anything. We'll never get back, well, not for 10,000 years, we won't get back to, the 1850 line, but that's a lot better. And so whenever we talk about our attempts to deal with this, we're talking about the difference between these two lines. In fact, these two error bars. So from up here to down there. So while some people think, oh, we can't do anything, we shouldn't even bother, it's like, no. Whatever we do will reduce this line closer to this line. And that's great. Okay. Anything you can do is good. So don't say, oh, well, we can't get back to 1850, so we shouldn't do anything. No, actually, this is actually quite important. So when we look at, Paris COP 21 or the recent Glasgow 26, I think it was, the only question is, are we going to do A2 or B1, and who's going to pay for implementing B1? That's the big, who's going to pay for it? Okay, so it's not going to be, the Philippines. It's going to be the United States, European Union, and China. We're the only ones that have the funding to do it. So that's pretty much the big question at any COP meeting. Now, in the United States, these effects, this is again B1 and A2. So in B1, which is the best we can hope for, in terms of CO2 reduction, so I mean, there's other things we can do, but in terms of CO2 reductions, this is the best we can do. And so again, you see the west side of the state of Washington is actually in decent shape compared to the rest. And this is in Fahrenheit. Because again, we are ameliorated by the marine climate of the Pacific. But again, if we business as usual, even we are not in good shape. So that gets pretty rough. Now, this is the last climate change slide, but this is from the IPCC. So, and it's still good. This is a couple of years ago. What this says is, in order to keep the change to 1.5 degrees C, or about 2 degrees C, or about 4 degrees Fahrenheit, you would have to reduce global emissions, between now and mid-century. So if we had started decreasing global emissions in 2011, we needed to decrease them almost 4% a year, which is a huge amount. By 2050, we could still have a fair amount of anthropogenic emissions, and that would have been okay. We blew that one. So 2015 comes around, and now we have to decrease about 5% a year. And we have to go to zero by 2050. Well, we blew that one. So 2020 came around, and it used to be in the future. I used to say 2020 is coming around, but no, 2020 is gone. And we needed to start reducing by almost 10% a year. And we had to go to zero by 2040. So when people talk about tipping points, they talk about 2040, because this is what they're talking about. You need to get to zero by 2040. And that's a steep line. And 10% a year is an amazing amount to cut. Now, usually if I had an audience here, I'd say, people wave their hand, how much have we been reducing? Yeah, it's a trick question, because we have not been reducing. We are still increasing. Now, the pandemic gave us a little bounce here and there, but we're back on track to increase global emissions by 2040. Every single scenario I've seen that's reasonable has us increasing and stabilizing up here. We're not down here. And so this is absolutely the wrong direction, and gives us a little pause. And so if this happens, we're going to have to institute a couple of other, plan Bs. And that's going to be even more difficult. So with that in mind, what do you think the fastest growing energy sources in the world are? So, and again, I usually have hands raised or that kind of thing.
You can type in chat. I'll read it.
So it's a trick question because it's fossil fuel. So the fastest growing energy source in the world in terms of, a kilowatt hours equivalent of consumption is oil, and then coal, and then gas. So this is absolutely the wrong thing. We keep, worldwide, now this is worldwide, not the United States, this is worldwide. So we keep building fossil fuel plants because we need energy. I mean, there's a lot of people out there, there's 1 billion people that have no access to energy whatsoever. 2.4 billion still burn wood and manure as their main source of energy, and 3 billion more people will be born by mid-century. So that's a lot of people. You need to give them energy. It takes about 3,000 kilowatt hours per person per year to raise someone up out of poverty. So if you want to eradicate global poverty, we're going to need more energy, not less, more energy. And if we're going to address climate change, we need more energy that are not these three, that are these three. So when you hear people talking about, oh, they don't like wind, or they don't like nuclear, or they don't like hydro, that's nonsense, because that's the only things we have. Okay, these are the alternatives. And if you're going to think that you're going to increase these way up here in time to do anything, then you need to bring all of them on. Nuclear, wind, solar, hydro, everything. Okay? Oh, cutie. What a cutie. Otherwise, this is going to keep going. I mean, wishful thinking is great, but it doesn't, reality is much more important. So that's the reality of this. So what we need to do, let me get rid of that. What we need to do is get rid of these and bring on these, all of them. We do not have the luxury to only do the pet one you like. Okay, and not do the one you don't like for ridiculous, obvious reasons that are usually wrong. So again, got to bring all of these up, and we got to get rid of all of these. It's actually simple, but not easy. So let's get to the Pacific Northwest. We are facing a significant generation capacity shortfall in the next 10 years. So between now and 2025, when we close our last coal plant in Washington State, we are going to have at least a 7 gigawatt shortfall. Now, a gigawatt, and I hate these terms, okay? So gigawatt is a capacity, okay? That means if everything's working great and sun shines 24 hours a day and all that kind of thing, you talk about 7 gigawatts, which is 7,000 megawatts. But it's, it depends on what source it is, because then you have to talk about capacity factor, which we will, and how much energy will this actually generate? And it depends on what kind of generation it is. They're all very different. So anyways, but in general, on average, we're going to be lacking about 7 gigawatts. Now that is about 2 Grand Coulee Dam worths. Okay, so the power output of Grand Coulee Dam, which has the highest capacity of any generating facility in America, 2 of those we are going to be facing a shortfall. And then by 2030, it's going to grow to 10 gigawatts. And that's, like 3 Grand Coulee dams. So this is really scaring everyone in the industry. So the public utility districts, Bonneville Power Administration, all the RTOs and ISOs, they all are very scared because we had a plan to deal with this, and that plan was crushed by legislation in 2019, which we will talk about. So this was recently, driven home in the June heat wave, of last year, where Washington and Oregon came extremely close to having rolling blackouts. Now, the Pacific Northwest does not have rolling blackouts because we used to have so much capacity, especially with hydro, which is wonderfully flexible. And we are losing that now. This is a problem. For similar reasons, California, Texas are having rolling blackouts every year during extreme weather, both heat and cold. And last a year ago, Texas had a cruel blackout that killed hundreds of people and cost them tens of billions of dollars in damage because they were told to be prepared for this, but they were not prepared for it. And the same thing with California. Now, when we talk about the Pacific Northwest from an electric grid standpoint, this is what the Pacific Northwest is. Okay, it's a little more than we usually think. So yeah, Washington, Oregon, Idaho, what we usually think of, but it also includes all of Utah, part of Wyoming, and part of Montana. So again, this is a rather large region that is connected with the grid, and you play off each other in terms of power, ramping up and down different power generation facilities. Oops. So one of the power grid reliability concerns, in 2019, the Washington State Legislature passed the Clean Energy Transformation Act, CETA, I'll talk about that a few times, in 2019, which requires that all utilities eliminate coal by 2025, it's only 3 years from now, and provide carbon neutral electricity by 2030. Now, carbon neutral electricity sounds good, but I mean, what that means is if you want a gas plant, you better be able to do carbon capture, and we don't have that yet. And so this basically eliminates gas. So eliminates coal and most likely gas. And a lot of the stakeholders and utility people and industry people said, oh my God, if you lose these base load sources from around the Pacific Northwest, not just Washington State, then you're going to increase the probability of brownouts and blackouts if demand increases, which of course it is. So if we look at the coal plants that are retiring in the next several years, these are them. We're going to lose 6 gigawatts, so 6,000 megawatts. And that's a lot. That's a lot of coal to lose, because coal, whenever we needed energy, we would buy coal energy from Oregon, from Montana, and from Utah. And those are all closing. I mean, they're all closing. So we won't be able to buy that anymore when we need it. And that is what is causing all these problems. Now, there's another 6,000 megawatts that's not shown here that's in Utah. So in Utah, the Intermountain coal plant is closing in 2025. It's a huge one. And the others, they were planned to close in 2040 and 36, but most Utahns want to speed that up and close them by 2030. Okay, what are you replacing it with? And of course, we're not replacing it with much at all. Now, I should mention that electricity is simultaneously, this has to be balanced. It is produced, delivered, and consumed in the same second. All right. So if you produce more than you consume, you start blowing transformers and causing fires. Okay. If you consume more than you produce, then you start having blackouts and brownouts. Now, the difference between a brownout and a blackout is that a brownout is purposeful. the utility companies purposefully cause brownouts in certain areas because they know they don't have enough generation to keep in it. So they decide, it's a tough decision, what to close down, what area to shut off, and all that kind of thing. Blackouts are simply, you don't even have any choice there. You just start blowing things and everything starts shutting down. So that's the difference between brownout and blackout. Now, I really want to talk about capacity factor. This is incredibly important. It is never talked about in the general media at all. The capacity factor, by definition, is the annual average percentage of the maximum output possible. So if you have a 1 megawatt wind turbine and it operates 30% of the time, then its capacity factor is 0.3 or 30%. And that's just what it is. There's really nothing you can do about it. Installed capacity then times this capacity factor times 8766 hours per year equals the amount of power produced per year from that unit. I mean, that's it. A little bit more, a little bit less, but that's it. That's what you get. You can't double that or triple that or anything else. You can lower it if something happens, but that's pretty much what you have. So if you look at the capacity factors for each of the 6 big sources of energy, then it's very interesting. So now these are historic averages. This is what's been happening, okay, in the last several years. So nuclear has always had a high capacity factor. I mean, it took us a couple of decades to get our act together in terms of how much time it took to refuel, because nuclear only refuels once every 2 years. And during that refueling outage, which just takes about a month, you do all the other upgrades and maintenance. So nuclear operates 90% of the time or more. Okay, our nuclear power plant out here near me, Columbia Generating Station, operated by Energy Northwest, last year had a 99% capacity factor. Okay, they just produce power all the time, and that's good. You can depend on that. You need that. Then natural gas is only about 57%. Now you might say, why is that so low? Well, yeah, I mean, theoretically, it could be much higher. Some plants actually operate at 70% capacity, but it turns out natural gas is expensive to run, contrary to what everyone says. Okay, natural gas, while it's the cheapest it's ever been, is still expensive. Okay, and the thing about natural gas and coal is that you have to fuel them all the time. Okay, it's all about the fuel. The cost of these is all about the fuel. Nuclear fuel is cheap. The nuclear fuel could double or triple in price as it has over the years. Never affects the cost of nuclear because it's such a tiny percentage of the cost. And of course, wind, hydro, and solar have no fuel costs. So the fuel costs determine the capacity factor of natural gas and coal. And again, coal barely is ever more than 50% of the time. I mean, there's a lot of maintenance, a lot of fueling outages, but it's just costly to run them all the time. And the other thing is that natural gas is used as a peaker. Okay, it's called peaker, which means throughout the day and throughout the year, the demand of energy on the grid varies wildly. So when it's really cold, everyone fires up their thermostats and all that kind of thing. And in the summer, they fire up all their cooling systems. And so you have sometimes a huge draw upon the system, and that's when natural gas hops in, because you can turn natural gas on and off fairly easily, easier than anything else except hydro or small modular nuclear reactors. And so suddenly they fire up natural gas plants and to take care of that excess. So if we get rid of gas plants, again, what's going to take care of that excess? And also in most parts of the country, energy is unregulated. Now, fortunately, in the Pacific Northwest, we are a regulated energy grid, which is wonderful. I love regulations. You need regulations. Okay, so we cannot be gouged. When it's really cold or really hot, the utility companies can't gouge us, okay, just because they can. Whereas in places like New York and New England and other parts of the country, they can. Okay, it's unregulated. So when Texas had that huge cold spell, the gas companies just gouged the public. I mean, they would charge them an extra $1,000 a month to get through that cold spell. I mean, that's disgusting. People are still reeling from that. And it's because they can, because it's unregulated. Okay, and it should not be. Something that's so important as energy across the country should be regulated across the country, but it's not. And then hydropower, the reason hydropower is only about 40% is because hydroelectric dams, the water is used for many, many things. Okay, I'm not sure if I have a slide on that. No, I don't. So, hydropower, the water in the river is used for irrigation, it's used for transportation, it's used for flood control, it's used for recreation, it's used for salmon habitat. I mean, it's used for a lot of things. So the hydroelectric dams in Washington State they're not allowed to run much more than 40% because the water is used for other things. Okay, so I want to, that's very important. And then wind, it's simply however the wind blows. Okay, so you're stuck with whenever the wind blows. And this is a national average, 34%. But in Eastern Washington, the capacity factor is only 27%. Okay, and in Tornado Alley, up through the middle of the country, the capacity factor is 45%. And that's really important. You can get almost twice the amount of energy if you put your wind farms in Tornado Alley than if you put them almost anywhere else. Okay, so it really matters where you place your energy source. The same thing with solar. So this is a national average. But again, if you're in the southwestern United States, you're going to have capacity factors that are 30, even 35%. And but solar in Washington State doesn't make a lot of sense, even over here. I mean, the solar panels on my roof only get capacity factor of 10%. That's pretty, horrible. But I wanted, solar panels. I wanted some street cred in solar. So I put them up there, but they don't produce much energy. And again, where you put these is important. So back to, let me get back here. So back to what is produced. So if you're going to compare any of these sources with each other, you need to normalize it. You need to compare apples to apples. And no one ever does. I mean, truly, your view of the cost of each of these is probably completely wrong. All right, because no one compares apples to apples. So if you have installed capacity times, whatever the size, like a 1 megawatt wind turbine or an 8 megawatt wind turbine or 1,000 megawatt nuclear power plant, that's the installed capacity. Then you multiply by the capacity factor and then times the number of hours per year, and you get the amount of power produced in megawatt hours per year, or if you want to do it in kilowatt hours, whatever. I like kilowatt hours because that's what comes at the end of the month in your bill. Okay, you pay 8 cents a kilowatt hour in Washington State on average. And every state is very, very different because every state has a very different power mix and it's either regulated or unregulated. So if you look at a nuclear power plant with 1,000 megawatt installed capacity, a capacity factor of 93.5% on average, and then 8766 hours, that nuclear power plant, like the one right out here near me, produced 8 billion kilowatt hours, 8 billion kilowatt hours, 8 million megawatt hours last year. And that's about what you expect. Okay. So when you think of a nuclear power plant, it usually gets about 8 to 9 million megawatt hours a year. Now it's the same installed wind farm. So you have either 1,000 1 megawatt wind farms or 128 megawatt wind farms. It doesn't matter. The total installed capacity of 1,000 megawatts times 0.27 for Washington State times 8766. That same installed capacity as nuclear will only produce about a quarter of the energy. So about 2 million megawatt hours per year. That's all. That's it. I mean, that's what you get. So if you're comparing these, you need to compare 4,000 megawatts of wind turbines with one nuclear power plant. But it gets even worse, actually, because if you compare the lifespan, so nuclear design life is 80 years, not 40. You probably heard 40 years. That was just a regulatory time period that was established by the AEC, in the 1960s. They just pulled that out of the air. They said, well, when should we relicense, really look at the nuclear plant in absolute detail as though they were a new one that we're trying to license? And they said, 40 years and then 20 years each after that. But the actual design life is 80 years, just like the design life for Grand Coulee Dam is 150 years. All right, so these things last quite a bit. So if you look at nuclear, then over its lifespan, this nuclear power plant out here, if it gets 2 more relicenses, as it should, is going to produce 655,000 megawatt hours or 600 billion kilowatt hours in its life, and that's what it's going to do. Wind, the same amount, again, 1,000 megawatts per year. They only last about 25 years. Actually, the blades don't even last 15 years. But again, we'll give them 25 years. They're only going to produce, about 60 million megawatt hours. I mean, that's a tenth. So when you're comparing wind and nuclear, you have to compare 10 times the amount of installed capacity of wind to nuclear. You have to do that. You cannot compare these systems without understanding that. So if you look at natural gas, their lifespan is, their capacity factor is 56% or so. Their lifespan is about 40 to 50 years. Same with coal. Hydropower, the big ones are, again, 80 to 100 years at least. Wind, 25 years. Solar, 20, 25 years. So this is important. You have to keep capacity factor in mind. Now, something called load following. So if you have a fair amount of wind or solar, they're called intermittent because you really can't depend on them. Wind especially, because it only produces power, significant power, when the wind is blowing between 30 and 40 miles an hour. Okay, it doesn't produce much if the wind's only going 5 to 10 miles an hour. You can still be turning, but it just won't produce very much. Same thing with solar, although solar is much more predictable because you know when the sun's going to rise, you know when the sun is going to set. Cloud cover and bad weather are things you can't really predict very well, but that's that. So where you have wind and solar, you have to have something to back it up, to load follow it or buffer it. Those are the two terms that we use. So when the wind stops blowing and you have like 7,000 megawatts of wind in your state, then suddenly you're going to need 7,000 megawatts quickly. Okay, I mean, in minutes. Usually natural gas is used to buffer wind and solar, or coal in China and Germany and parts of the Midwest and Texas. Now, in the Pacific Northwest, we use hydro. Okay, also parts of China and Eastern Canada, we use hydro. So all of our hydroelectric dams are very flexible. You can be producing power, and if you need to stop producing power, you can just push the water over the dam, period, and stop producing power. Or if you are pushing it over the dam, over the top, and you need the power, you can suddenly switch and put it through the turbine. So, hydro is used to buffer the intermittency of the grid in the Pacific Northwest. Now, pumped hydro storage is 97% of global storage is pumped hydro storage, and pumped hydro. I'll get to that a little bit, but essentially, it's a fake river, okay, with a hydroelectric plant attached to it. So you pump, you use wind and solar energy when it's produced to pump water uphill, maybe 300, 400 feet, into a reservoir that has a hydroelectric dam associated with it. And when you need it, when the wind stops blowing and the sun sets, then you let that water out and run a hydroelectric plant to produce electricity. It's about 90% efficient, which is pretty good. So you don't lose much of the energy from the wind and solar. And that's great. That is absolutely a wonderful thing to do, except every time we propose it, the public shoots it down. I don't know what they think is going to happen. You need things like pumped hydro storage to deal with the intermittency, to store energy, because we'll never have enough batteries. We don't have enough lithium in the world, especially if we're going to bring up electric vehicles. It's foolish to try to use batteries to store huge, grid scale energy. It just is dumb, and it won't happen. So, but pumped hydro storage is great. But again, we don't do it because people don't understand we need it, and so they keep shooting it down. Now, there are new gravitational potential energy storage systems. I'll talk about that. They're like pumped hydro, except instead of moving water, you move mass, like 35-ton bricks up 300 feet and then drop them when you want to recover that energy. And the new small modular reactors are specifically designed. New small modular nuclear reactors are specifically designed for load following wind and solar. I mean, they're absolutely perfect, better than gas, and you don't need to have them idling. Now, in the Pacific Northwest, where hydro is used to buffer, we're having problems when we have droughts and heat waves, just like last year, okay? That put us, last year put a stress on the system to near the point of failure. BPA said it was lucky they didn't have to implement rolling blackouts specifically because of the lower 4 Snake River dams. So when people talk about decommissioning the 4 Snake River dams, what are you going to replace it with? Because they buffer wind. So if you replace dams with wind, you lose buffering capacity as well as total capacity. So this is not a simple issue, and we won't do it by being political. So this is something called a load balancing graph. This is for the Pacific Northwest. This is from the Bonneville Power Administration. They do these every week. So this is a week. And let me just go over this. So the gray line is load. So that's what the demand out of the grid is from the public and from industry. So again, you can see in the morning, the demand shoots up because everyone wakes up and starts, making coffee and all that kind of thing and start getting ready to go to work. And then it drops during lunchtime, basically. Then it goes back up again, and then it drops during the evening. So this is repeated every single day. There's this kind of double hump for load. I mean, it's just the way it is. Now, the light blue line is hydro generation. Okay, so the hydroelectric dams, of which we have so many in the Pacific Northwest. So here, as load goes up, hydro goes up. Load goes down, hydro goes down, up and down. It mirrors the load. Okay. Now, the red line and the pink line are what we call thermal plants. So thermal plants just mean you're heating water into steam that then turns a turbine, and that's that. So that's mainly fossil fuel, coal, gas, and biomass, and then nuclear. So again, these just produce power, when you think you're going to get that. They're very predictable. Okay. And they don't change much. Okay. We don't use those to load follow. And here's wind. Now we have a fair amount of wind in the Pacific Northwest. In Washington State, we have 7,100 megawatts of wind. So when wind comes on, you notice right away that hydro goes down. Okay. So in fact, hydro plummets when wind comes up. Okay. And then wind goes down and hydro goes back up, and then wind comes up and hydro plummets. All right. So wind is displacing hydro. Hydro is used for load following wind. All right. And what that also means is that wind is not displacing fossil fuel. All right. There's no climate change advantage to wind in the Pacific Northwest because it doesn't replace coal or gas like it does in the central United States. Okay. So wind in the Pacific Northwest is basically useless. And worse than useless, because it's wasting resources. When you dump water over the dam, you actually dissolve more nitrogen in the water, which is very bad for salmon. And you're wasting that. You're wasting that energy. So again, wind does not contribute in a carbon sense, in lowering the carbon output of our grid. It doesn't change that at all because it's simply displacing another renewable, hydro. So this is really key. This is not, when everyone talks about building wind farms in the Pacific Northwest, they think they're doing good. They think they're displacing fossil fuel, but they're not. They're displacing hydro. And we're closing our fossil fuel plants. So they'll never be able to displace fossil fuel because we're getting rid of them all very shortly. Now, the Northwest Power Pool, which is a conglomeration of all the generators and public utility districts and BPA, that kind of thing, they have always considered an outage risk, so a risk of blackouts, less than 5% to be safe, meaning if it's less than 5% likely to have a blackout, you're probably never going to have a blackout. Okay, that's fine. We had enough capacity. But now they warn that we face a 26% probability of an outage by 2025. And that is disastrous because 26% risk means you will have blackouts. It's not like you won't. You will have blackouts because this is 26% continuous. So yeah, most of the time you're not going to have blackouts. But when you are hit with a really hot weather or really cold weather, that's when stuff happens, okay? Because things don't operate very well in the very cold or very hot. Wind does not generate anything when it's cold or very hot. So they're worried, as they should be, because they're responsible for providing this power and for preventing blackouts. Now, the increased load to generation, why this is going to happen is because we are losing all the coal plants, like I mentioned. We have an actual increase in population. We have not increased in population much in the last 30 years, but now we are, all right? Yeah, everyone wants to move to Washington State. It's a great place to live. and an expected large increase in electric vehicle use. Now, the only way to get rid of petroleum is to go to electric vehicles. You can talk about hydrogen all you want. No, it has to be electric vehicles. That's going to take a lot of lithium, it's going to take a lot of cobalt, and it's going to take more electricity. So just electric vehicle use itself in Washington State, if you want to significantly get rid of petroleum, you're going to have to provide an extra 10 billion kilowatt hours a year, which is as much as the nuclear power plant here produces. All right. And, or you could build a full SMR set or 2 gas plants. Okay. But we can't do gas because of CETA now. So you're stuck. So you either build nuclear or you either build more hydro or you build more nuclear. That's it. Building wind isn't going to help this because we use hydro to balance wind. So you get no overall benefit. Now, the problem with wind, of course, we talk about a general capacity factor of 30% or so, but what's most important is what happens during really bad weather. So when you need that energy, you need to be able to access it. And if you're looking at coal or hydro or nuclear or something, to provide that energy when you need it, you can depend on it. But wind, you cannot. So we do these resource adequacy studies every few years, and the last one in the Northwest basically said that Washington's 7,100 megawatts of wind power was determined only to be 7% available. That is, 500 megawatts of wind power out of 7,100 megawatts can be expected to show up on the grid during the coldest or warmest days of the year. That is not good. That is what caused the blackouts in Texas, contrary to what you've heard. And we can go over that if anyone has any questions about Texas. Now, if you look at all of the leading climate scientists in the world, Jim Hansen, everyone knows Jim Hansen. He's the guru of climate change. He's the one that went before Congress in the 80s and 90s and said, please, we need to deal with this. And then Carrie Emanuel, Tom Wigley, Ken Caldera, all of the top climate scientists in the world said this, okay? There is no credible path to climate stabilization that does not include a substantial role for nuclear power, not just existing amount, but expansion. Okay, they've done the math. We can't do it without nuclear. And of course, those of us in the business know that. And you can't do it without wind, and you can't do it without solar, and you can't do it without hydro. Okay, you need all of the alternatives. You don't have the luxury to throw anything out. Now, we're going to get into nuclear a little bit, and Paula said that most people don't understand nuclear, which I understand very well. Most people don't know it. It's not taught in school or anything like that, and it's not very intuitive. So we'll go through a short nuclear primer. So uranium-235 splits easily. Uranium-238 does not split easily. Now, natural uranium ore is only 0.7% 235. It is mostly 238. Now, it exists as a rock. It's a rock. So you mine it like you mine for iron, and you smelt it, and you get something called yellowcake, which is uranium-308. And that is, again, 0.7% 235 and 99.3% 238. In order to maintain a controlled chain reaction or even an uncontrolled chain reaction, you need to enrich that to at least 4%. Okay, so you go from 0.7% to 4%. So you're basically increasing it by 50 or 60 times. It's still mainly 238. So if you want nuclear fuel for a power reactor, it's still mainly 238. Okay, now if you want a bomb, it's going to be all 235. Okay, and we'll talk about why. But that's different. So if you want to bomb, all 235, and the same thing holds with plutonium. You only need a couple percent of plutonium to run a nuclear power plant, but if you want to bomb, that's what Hanford site was all about in the 40s, 50s, 60s, 70s, and up to 83, then it has to all be uranium-235 or all plutonium-239. Now, so what happens is you have uranium-235, a neutron comes in and splits it into two unequal pieces called fission products, 3 neutrons out, and a little bit of energy. Okay, 3 for 1, such a deal. That's why this works. Now, what happens if you're a bomb is that you're still all uranium-235. Okay, so what those neutrons see in general is another 235. All right, and then that splits. And so now you're at 9 neutrons. So 9, 27, 81, boom, in a microsecond, you're at 6, times 10 to the 20 neutrons in splits. And that's where your power is. It's a blast. There's nothing to do with radiation. Okay, a nuclear bomb, the effectiveness or the horror, the power of a nuclear weapon has nothing to do with radiation. It's a blast. Because what happens, the speed at which these two pieces fly apart is what gives you your pressure and your temperature. So you get up to the surface of the sun type temperatures and pressures that are enormous, and so that's what causes your blast. Now, if you are not a bomb, then you only have a little bit of 235. And so those 3 neutrons that come out generally do not see another 235. They see mainly 238 because the fuel is 96% uranium-238. And so it doesn't split, but captures that neutron and quickly double beta decays and forms plutonium-239. You're breeding plutonium-239 from uranium-238. That term breeding is what is this referred to, okay? So you need neutrons to breed, okay? So neutrons are the only thing that can make something else radioactive. Other, gamma rays, alpha, beta, they can't make anything radioactive, but neutrons can. So neutrons, are captured by this nucleus of 238, okay, becomes 239, and then decays away to 239 plutonium very quickly. Now, after 2 years, you've bred so much plutonium, which gets burned immediately. I mean, it gets burned immediately. That you're making more of your power from that fuel is coming from plutonium than it is from uranium-238 after 2 years. Now, after 6 years, so much of these fission products, this junk, builds up in the fuel and starts scarfing up all the neutrons, and the thing fizzles out. It's not done. It's not spent. It's not used up. It simply has too much junk in it. Okay, so you've only used about 5% of the energy in that fuel, but now it has too much junk in it. So you can reprocess it, get rid of the junk, recover the uranium and plutonium and make new fuel out of it. France does that, England does that, Japan does that. Or you can just, put it aside. You will use it in the future in fast reactors like Bill Gates is designing. So whatever, but it's spent fuel is not spent. It's just got too much junk in it. Now, this brings to mind nuclear waste, okay? Because the fission products, these pieces, are the only thing that's really highly radioactive in spent fuel, okay, or in nuclear waste at all. So these are gamma emitters, strontium-90 and cesium-137. They're gamma and beta emitters, and they're hot. I mean, their half-life is 30 years, so 7 years, 7 half-lives to background is a rule of thumb. So after 210 years, let's say 300, round up, the waste is not very radioactive. Okay, you could hold it in your hand. I mean, it's no big deal because the gamma emitters are all gone. Now, when you take fuel out of a reactor, you put it into water for about 5 years because they're really short-lived stuff that's only, has, a month half-life or not even a year half-life. Those are the really hot stuff, and they're gone in 5 years. So after 5 years, you take the spent fuel out of the pool and you put it in dry cask storage while these two decay away over the next 200 years. Now, again, those are the hot stuff. Then you have the not so hot stuff. Now, you can hold plutonium in your hand. You can hold a chunk of plutonium in your hand. It is not going to hurt you. You can even eat some of it and it won't hurt you. You have to powder it and breathe it in order to have any effect. Same thing with uranium. And mainly those effects are heavy metal like lead and mercury, not the radiation, because the radiation is very mild. It's very low level radiation. So all of these actinides, so this is, the neutron capture, the breeding, breeds not just neptunium and plutonium, but it breeds americium, it breeds other things as time goes on in the reactor. And so those things have very long half-lives, thousands of years, millions of years. Uranium-238 half-life is, 4 billion years. And the activity, the radioactivity, is inversely proportional to the decay life, so the half-life. So again, if it's really active and it's really throwing out a bunch of radiation, then it's going to decay away fast. Okay, so things with short half-lives are really hot. Things with long half-lives are not, because it's just by definition, they're taking a long time to decay away. So they only put out, a couple of bursts of radiation every once in a while. They're not just super hot like cesium-137 is. So these are very long-lived, but not very hot waste. That's important. Now, this is for nuclear energy. If you're making a bomb like we did at Hanford site, Paula, tell me if I'm taking too long on this, but if you want a bomb and you want plutonium, because plutonium is more effective as a bomb, you can put it on a missile. You can't really put uranium-235 bomb on a missile. So you want plutonium. That's what we've always wanted. So what you do, though, is you can only run it in the reactor, in a weapons reactor, not a power reactor, a weapons reactor like we had out here. We had 9 of them. They couldn't produce energy even if we wanted them to. They were for weapons. Like Chernobyl was actually a weapons reactor. So you would only keep the fuel in the reactor for 6 months. If you left it longer than 6 months, you would start breeding in neutron poisons like plutonium-240 and 242 that don't split. They simply scarf up the neutrons. And so if you need a bomb, you cannot let this fuel stay in the reactor for more than 6 months. You take it out and you dissolve it up and remove your plutonium, but you only can keep it in the reactor for 6 months. All right? That's how you make a bomb. Bombs are completely different than power. So completely different reactors, completely different operations, and how long you leave the fuel in. Okay, so now we're talking about small modular reactors and advanced nuclear reactors. So there are 10 very good designs for advanced reactors and small modular reactors that have either applied for NRC or in the process of applying to NRC for licenses. So the best one, the one that's most farthest along, is NuScale out of Oregon. So Oregon State University, Jose Riaz, brilliant nuclear physicist, he's been doing this for years. He designed a small modular reactor. So it's like a big reactor, except it's small. Okay, so you shrink the core size down dramatically, and then your surface area to volume ratio goes way up, and you can't melt down. Okay, this is incredibly important. So that's NuScale. Then each of these has their own. X Energy is another good one. It's a Pebble Bed Reactor, and then TerraPower is Bill Gates's reactor. Now those 3, NuScale, X Energy, and TerraPower, are the 3 farthest along and the 3 most likely to be built in the next 10, 15 years, and most likely to be built in Washington State. So now, the whole idea of small modular reactors is that they are better than anything else at buffering or load following renewables, like I mentioned. So SMRs can't melt down, and all the other scary stuff, we fixed. We haven't been idle in the last 30 years. And plans exist for at least 2 of these in Washington State. So if we look at TerraPower, it's a sodium fast reactor. Now, the thing about a fast reactor is that you can use old fuel from the old reactors, and you can burn that up and get 10 times as much energy out of it. And then all you're left with is the short-lived fission product. So the waste is much, much better. It's gone, it's not radioactive after only 300 years. Now, X Energy, they have a Pebble Bed Reactor, and the pebbles can't melt down, very nice, and it's easier to deal with the waste. And then NuScale's SMR, small size, large surface area to volume ratio, prevents any kind of meltdown, and the plant is very small. All of these plants are very small. You don't need to have 50-mile evacuation zones and that kind of stuff. So if you want to look at what TerraPower's design looked like, and almost all of these have the core buried in the ground. So this is the ground surface, and this buried in the ground now. And we realize that the the earth, the soil, and everything else is a great heat sink. So again, in terms of preventing meltdowns, you need to be able to get rid of heat for about a week. Then it's cool enough that it can't melt down. So here's X Energy's Pebbles. So it's just a unique. We actually built all of these as test reactors in the last 50 years. We know they work. We just haven't commercialized them until now. So again, you have the fuel is a kernel, and it's surrounded by a bunch of different layers that prevent it from melting down, period. And it's really nice. These are about the size of golf balls. And you can, when they go through the reactor cycle, you can take them out. If they're not used up, you put them out back on top. It's kind of neat. And then NuScale, again, small plant size, can't melt down. So that's it. It's not even a square mile. Excuse me. There have been some awards. So TerraPower, Bill Gates' reactor, got I think it was a $30 million award from DOE to start working on it in real. And they actually decided to look in Wyoming to replace coal plants. So the nice thing about siting an SMR in an old coal plant is that you can use most of the infrastructure of that coal plant. You can use the high voltage transmission lines. Again, you're just heating water into steam to turn a turbine. So the turbines are still fine there, the steam generators. So, you're simply replacing the source of energy, the source of heat that produces the steam that turns the turbine that generates electricity. So it's really ideal for replacing coal plants. And also coal plants are sited where they needed to be a long time ago when they were sited there next to or near large population centers that need that energy. So you don't have to build hundreds of miles of new transmission lines to take that energy, say from a wind farm or something, to where it needs to be used in like Seattle or Tacoma. Again, X Energy also got a very nice award. This is supposedly going to be built here near me in Richland, Washington, on the site of Energy Northwest nuclear power plant. And so they fit under their existing license and their permits, so it's a lot easier. They have the people there already and the knowledge. And then NuScale is going to build its first power plant in Utah to back up UAMPS, which is their version of the Public Utility District, to back up their new wind farms. And they got about $1.5 billion to start that process. Now, again, I talk about can't melt down, and this is why we talk about a small modular reactor like NuScale. You're simply shrinking the core, so it's a lot smaller. So the surface area to volume ratio is so much higher that the heat bleeds off quickly. And if all power goes out, no pumps, no power, no external water, it simply just cools off. The water evaporates, and by that time, you're done. It can be just sitting in there indefinitely. So cannot melt down. I want to go over the cost of energy a little bit. This is a great study done by Carrie King at UT Austin that looks at the cost of energy, again, normalized to the gross domestic product, so GDP. And it's kind of hard to compare someone in the year 1300 with someone in the year 2000, but hey, it was done quite nicely. Now, in the past, okay, all of your energy came from muscle, right? Food was your fuel, your energy fuel, okay? So whether you were feeding humans to do the work or you were feeding oxen and horses and stuff to do the work, it doesn't matter. Everyone was getting energy from the transition from chemical potential energy in your food to mechanical energy in your muscles. Now, about 1850, coal came into use, and that changed everything, okay? The nice thing is that, one, you didn't need slaves. You didn't need to own someone to get 3,000 kilowatt hours per person per year. You just needed to burn coal, and that changed everything. So, and of course, it was cheap. It was cheaper than humans. And then here's a little spike from the the 1973 oil embargo, which is nonsense. It was totally fabricated, but it was real in terms of cost. And so where we are now, fuel has never been cheaper in the history of humanity. Energy, I'm sorry, has never been cheaper than it is now. Never been cheaper. And because of energy is so cheap, food is so cheap. Food has never been cheaper on a GDP basis than it is now. Yeah, we're having a little bit of inflation right now. Okay, it's still cheaper than it's ever been. So if you're going to make these major changes, you're going to get rid of fossil fuel and everything, then now is the time to do it because energy is so cheap and it won't stay cheap. So again, how much is a new energy mix going to cost? Now, these, I should probably turn on a light here. I'm sorry.
Oh, I had
sorry.
myself muted. I was about to address, but thanks for noticing, Jim. I
It's
didn't
getting
want to
dark.
interrupt you.
It's getting dark in here. So
Yeah.
so anyway,
Go ahead.
so there's something called levelized cost, and it's what everyone uses to compare, apples to apples. Although it doesn't compare apples to apples, like I mentioned before, but that's okay. I hate levelized cost because it includes a bunch of stuff that's like depreciation schedules. I mean that's an arbitrary thing. Okay, the depreciation of an asset. I mean it's like, okay, well you can make all assumptions you want to make, but that's something that can be changed. That has nothing to do with the actual source of electricity. So, but state legislatures use levelized costs to make decisions. So it's important to do. So these are levelized costs from the Northwest Integrated Resource Plan. So this applies mainly to the Pacific Northwest, a little bit different elsewhere, of course, depending on regulations and everything else. So in the Pacific Northwest, this is the cost per kilowatt hour, cents per kilowatt hour, to produce the electricity. Okay, now, like I say, we are regulated. So utilities only charge 8 cents a kilowatt hour on average. So they're not making a total bunch of profit here. Okay, and unlike in in New York State, where they gouge the consumer and they make huge amounts of money. So not very profitable in terms of, if you want to get filthy rich, energy in the Northwest is not the way to do it. Now, what's funny here is that these four sources are within 1 cent of each other. All right, that's just not very much. So you have to ask yourself, is 1 cent worth making bad decisions? Okay, I know someone has to make a buck. This is America, I get it. But if you're going to make a decision and you say, oh my God, well, gas is the cheapest thing, so we're going to go with gas. Yeah, well, it's only 0.4 cents cheaper than wind, and a penny, 1.2 cents cheaper than nuclear on this scale. It's like that's not enough of a difference. I mean, if you don't want to spend an extra penny per kilowatt hour, then you don't care about global warming. I'm sorry. Okay, you have your priorities totally messed up if you think a penny a kilowatt hour is enough to throw out any energy source at all. Now, coal's a little bit more expensive and hydro's a little bit more expensive, but we'll talk about hydro. There's a way to double hydro in America without building a single new dam. That's very important. Now, again, LCOE, levelized cost of electricity, doesn't capture what's called indirect cost or externalities. That's a term that means, yeah, it's not a cost that comes at the end of the month in your bill, but it's someone has to pay for it, whether it's your grandchildren, whether it's polar bears, whatever. Okay, someone's going to pay for this. And so you need to capture that cost as well. So ISH Market, which is a big analytical firm for energy, they determined this, and this is in the Pacific Northwest, and they came up with, okay, if you want to keep existing nuclear going, as you probably heard, we keep closing nuclear plants in America because, quote, they're not cheap enough. And again, they're only a penny more expensive than anything else. But if you want to keep existing nuclear, it's only costs 4.5 cents a kilowatt hour. the nuclear power plant out here near me, Columbia Generating Station, only charges 4.5 cents a kilowatt hour. Okay, by the way, people don't realize that Energy Northwest is a not-for-profit government agency. Okay, it's not a corporation. It's a state government agency, and they're not allowed to make a profit. So that's wonderful. So that's great. Now, new gas is 5.9 cents a kilowatt hour, unless you want it to be net zero, which means you need to capture carbon and all that, and that is not even an option right now, but it could be in the future. 6.9 cents per kilowatt hour for new nuclear. So if you're going to build these small modular reactors, they're about almost 7 cents a kilowatt hour. But wind is almost 9 cents a kilowatt hour. Okay. And this includes, taxpayer subsidies and all that kind of thing. And solar is even more expensive. It's almost 10 cents a kilowatt hour. Now, you have to remember that taxpayer subsidies do not reduce the cost. They simply shift that cost from the ratepayers to the taxpayers. And since we don't really know where our tax money goes, it seems to disappear into the ether. So, but don't be fooled. I mean, a subsidy, we pay for that subsidy. Okay, it's paid for in a different way, out of our tax money instead of out of our bills at the end of the month. Now, it matters where you put power plants. So I need to stress this. So, and one of the reasons is the amount of material it takes. So I want to go over this. It takes, this is volume of concrete, so, a meter cube per megawatt hour, and a mass of steel, metric ton of steel per megawatt hour. And you can see right away that the renewables use huge amounts of material. Okay, so wind uses 10 times the amount of steel and concrete that nuclear or gas does, or even coal. Solar uses a lot of steel, but not a lot of concrete. Hydro uses a lot of concrete, but not a lot of steel. And the thermal systems don't require much at all. And this is important. So when you see the emissions from wind, most of that emissions is from the construction. It's from concrete, which is very CO2 emitting, very, very bad. And it takes so much concrete. I mean, a 1 megawatt wind turbine takes, almost 1,000 ton meter cube, which is over a ton of concrete. So again, if you're going to site your wind turbines and you want the biggest bang for your buck, the biggest amount of energy for the amount of steel you're using, you better site it in a place that has a high capacity factor. Same thing with solar. So if you look at wind, here is basically a wind map, a wind efficiency map. So here's Tornado Alley. Now, Tornado Alley is termed Tornado Alley for a reason, okay? Not just a lot of tornadoes, but a lot of wind. Okay, it's always blowing there. So capacity factors for wind here are 45, even 50%. That's amazing. Okay, now if you're going to put them over here in Washington State, I wouldn't. I just wouldn't. It's stupid. Okay, you don't put wind where it's green. You don't put wind out here in Georgia, all right, or in Maine. I mean, that's a dumb place to put wind because you get half the amount of energy, but you're going to spend the same amount of money, and you're going to spend the same huge amount of steel. Now, I should mention that the amount of steel, we don't produce enough steel to build the amount of wind that we need. We have to buy that steel from elsewhere. In fact, the world doesn't produce enough steel to actually implement wind, any significant amount, like 20 or 30% of global energy from wind. We don't have enough steel. We don't. So, okay, we're going to have to, double, triple, quadruple the number of iron mines. Iron mining is not very nice. So again, there's a lot of other indirect issues that have nothing to do with the initial cost of the stuff that you think of, but that are important. And you have to plan for this. You just can't go willy-nilly throwing wind turbines up wherever you want to, even though you get a subsidy for it and people make a lot of money. That's the problem in America. It's driven by money. But if you want the most bang for your buck, this is where you put it. Same thing with solar. Oops. Yeah. So same thing with solar. Okay. You don't put solar cells or arrays in the green. and yellow isn't all that great either. You put it in the red and the orange, okay? That's where you get most of your energy. So if you're going to use, again, a huge amount of steel for solar, it doesn't take much concrete, but a huge amount of steel, you better put it where you're going to have capacity factors that are twice what they are in like coastal Washington and Oregon. So that's why, the Mojave Desert here, that's why California has installed so much solar in the Mojave Desert. Okay, it's very efficient. Problem is, they only installed solar and they didn't install anything to back it up. So now they're having major problems. Now, DOE and the National Hydro Association have a plan to double the amount of hydro capacity in the United States without building a single new dam, because only 3% of our 80,000 dams generate power. Okay. And of course, in here we have huge power. This is just showing the dams that are not powered. So if you're going to install all this wind, which you should along Tornado Alley, then hydro is a wonderful thing to back that up. And you could electrify all these dams. It is a lot easier to electrify an existing dam, because a lot of dams are there mainly for flood control or irrigation or whatever, transportation, and they're not there to power. But you can just power them up. It's a lot easier to power an existing dam than it is to build a new one someplace. Both the environmental impact statement's already done, the people that live near it are already used to it, and you're not changing anything else. Whoops, let me go back here. So this is very, very important. If you really want to get to a Green New Deal, you need to do this, okay? And you can double hydro in America without building a single new dam. Now, I talked about pumped hydro storage. Pumped hydro storage is you simply build a reservoir, that doesn't have water in it to begin with, but you build a dam, you build a reservoir, and you, during the day, when solar's running or when the wind is blowing, you pump water into that reservoir, and then when you need it, you let it back out, runs a hydroelectric plant, and you recapture the energy that you stored from the solar and the wind. It's very nice. Here's one. This is a pumped hydro storage. You can either use groundwater or you can use an existing river. Whatever is most convenient or most desirable, depends on what the rainfall is, blah, blah, blah. Kind of don't want to put these in deserts, but it doesn't really evaporate that much water. So it's pretty good. So again, this is a pumped hydro storage. The water is pumped up into this reservoir using wind, and then it's let out to produce electricity when needed. It's 97% of the storage in the world is pumped hydro storage. Now there's a new technology that's brilliant. It's the same kind of thing as pumped hydro. It's gravitational potential energy. You're lifting it up a gravitational well and storing it up there. So this is called the energy vault. And instead of using water, pumping water up to a height, it actually raises these 35-ton bricks. And the bricks are green bricks. They're not concrete. So they're very CO2. The very low CO2 emissions to build this thing. So again, during the daytime and right next to the solar array, you use the solar power to lift these bricks up 300 feet. And then when you need that energy, you let it out and it drops and it powers, a turbine just like, it powers a generator just like pumped hydro storage does, except it doesn't need water. So the Saudis are actually putting these in to support their solar arrays in the Arabian Desert. Sorry. Now, Washington State, we actually, because we're so hydro, we have so much hydro and nuclear and not much, only one coal plant left, it's closing soon. We have decreased our CO2 emissions from the industrial side, from the power side, a lot. There's not a lot left here to work with. I mean, once the coal plant goes, this is going to drop in half. What we have a problem with, of course, that everyone does, is transportation. Everything is still petroleum, either or, gasoline or diesel or jet fuel. So if Washington State wants to decrease its CO2 footprint, you got to deal with transportation. It has to be electric vehicles, and you need more electricity. So you can't, you've got to think about the amount of electricity it's going to take to power a transportation fleet. We're talking about 5 million electric vehicles. Well, that's a lot. And that's going to take 10 billion kilowatt hours a year at least. So that's the only thing that we can do better in terms of dropping our CO2 footprint. We already have the lowest CO2 footprint in the country. Now, then there's other things. Carl, Paula, how am I doing time-wise?
Time to wrap it up and let people talk about questions.
Yeah,
Okay,
we're
well,
at 8:20.
let's do that. So, yeah, I see a lot of questions I have not dealt with. So why don't we stop there? I mean, if you want to talk about the death print and all that other stuff, then we can do that as part of the questions. Thanks.
Great. And let me get us. So if we want to go over questions in chat first, or anyone else who I recognize, I'll let you turn on your camera or at least your microphone to ask a question. A few things in chat that we've got here, mostly commentary. So a question from Twitch chat was, what's the efficiency of carbon capture on fossil fuel plants? Is it incredibly efficient, or does it really greatly reduce their energy output and profitability?
It actually reduces, the efficiency, you lose about 5%, which isn't very much. I'm sorry, that's for scrubbing. I'm sorry. You lose about 10% of your energy. It's not that bad, okay? It's just that we don't have that technology. Now, why have I lost you?
I need to put myself back up on.
No, but I've lost Zoom totally, so I'm not quite sure what I'm doing here.
Okay.
Damn it.
Actually, it's okay because we can see and hear you. So pretend like you can see us, maybe.
Yeah, I probably lost just the. Oh, there it is. Okay, good. So carbon capture, again, great idea. Okay, we haven't done it very much because it's costly to set them up. I mean, running them, the efficiency in terms of how much energy it takes isn't the issue. It's setting them up, and we just don't have that yet. And I'm sure we will, but just like we can extract carbon out of the atmosphere, but it's just very expensive, and we would have to build 70,000 units to carbon capture, and we're just not doing that.
Great. So let's see. There's one question from Dan that maybe we'll hold. It's about the Snake Rivers. So sorry about that, Dan. Let's get to some of the new person questions. So someone comments that when Bonneville Power buys wind power at 15 cents per kilowatt hour, are they cheating customers, or what's the deal? Why is the spot price for wind that high?
Oh, because it's that high. I mean, it's not the customers that get shafted. It's BPA that gets shafted, because BPA cannot then charge customers anymore for that energy. Okay, we are a regulated grid, and so Bonneville Power Association and everyone else is only allowed to charge so much for electricity, even though they pay more for it from out of state or something like that. So again, this is the problem with being dependent on something else, someone else for your energy. They dictate the price to you. You don't dictate the price. And so if we have to, we never had to buy much energy from anyone else. Okay, we already had so much of our own, but we're losing that, and the surrounding states are losing that too. So now we're all going to be competing for the same excess energy from like British Columbia, or Mexico or whatever. I mean, where the heck are we going to get this energy when all the coal plants are retired in 2030? We used to get our excess energy from those coal plants, almost all of it.
So another comment basically is that you can use solar to make hydrogen. So can you tell us anything about what's the efficiency of hydrogen electrolysis and
about 17% efficiency. So for water. Now, again, we get hydrogen from methane right now. Okay, all of our hydrogen comes from natural gas because you can split the 4 hydrogens off of the carbon a lot easier than you can split hydrogen out of water. So everyone talks about hydrogen from water and it's all wonderful, great, but we don't do that because it's too expensive and it's not very efficient. It's only 17% efficient. So again, we're using methane to make our hydrogen. And so again, that's a fossil fuel. And it's okay if you like that. Okay, if you want to do that, it's certainly better than coal. I mean, if you need an evil, coal is evil. Okay, I mean, it kills a lot of people and it's really dirty and all that kind of stuff. Natural gas is a lot cleaner, but it's still fossil fuel and it still produces more than half of the CO2 per kilowatt hour as coal. So again, electrolysis is great, sounds great, but it's not efficient at all.
And Lila asks, coincidentally, is nuclear a good way of producing hydrogen?
Yes, it is, because it produces it operates at a higher temperature. So especially these fast reactors and these high temperature reactors, the new ones are incredibly efficient at producing hydrogen, as well as desalinating water. I mean, the same kind of thing, as well as providing high temperature for industrial uses. Okay, like they do in Sweden. So again, nuclear has a lot of benefits. It doesn't, the only CO2 emissions are from the concrete to build it, pretty much. And there's the mining. There's just so little fuel it takes that the mining is nothing as well. So it's just, and the small modular reactors are ideal for load following wind and solar. So you got to bring them all up. You're going to bring up wind. You're going to bring up solar. You're going to bring up nuclear. You're going to double hydro in America without building a single new dam. That's pretty much the only mix that you can come up with that gets us where we need to be by 2050.
So Tom asks, what is it about our hydro and our fossil fuel assets that means we choose to turn off the hydro instead of the fossil fuels?
Oh, well, yeah, and turning off hydro is stupid. I mean, I'm sorry, it's just stupid. But it depends on what the perspective is, what the political issues are. I mean, there's a lot of political issues, and there's a lot of different types of hydro dams in the state of Washington. There's a bunch of, like I mentioned, there's 1,080 dams in America. I'm sorry, in Washington State, and only 3% of them are powered. So when people focus on the Snake River dams, it's like, why are you focusing on Snake River dams? They have fish passages. There's hundreds of dams in Washington State that don't generate electricity, that don't have fish passages, that are much more harmful on salmon, and than the lower Snake River dams. I mean, I don't know why you're just focused on that. There's a whole bunch of other dams that are better to take down and easier to take down.
Do we have the same financial structure around hydro, the same benefits for putting it on the grid as wind and solar?
Oh, much more. I mean, oh God, yes. No, hydro is wonderful for the grid. That's why we've never had a problem.
Yeah, but no, I mean in terms of financial compensation.
No. So existing hydro doesn't get any benefit yet because we are not pricing carbon. You need to price carbon. Okay, then you get the full benefits of all the NARD carbon sources like nuclear and hydro. I mean, wind and solar have tons of subsidies in any way. Nuclear only needs 1 cent a kilowatt hour. I mean, come on, that's nothing. Wind and solar get over 2 cents a kilowatt hour of a subsidy, and hydro should get a penny or two as well. But if you don't price carbon, then you're not really dealing with the issue.
Let's see. Jim says he had no idea that there are still nuclear power plants even operating in the U.S., let alone the state of Washington.
Oh, okay, I'm sorry. I don't mean to laugh. 20% of our power, okay? It is the third largest power producer in America. Behind natural gas is 1, coal is 2. So natural gas is about 40%, coal's about 30%. I'm sorry, coal's about 19%, and nuclear is about 20%. So yeah, so nuclear is in the top 3. I mean, it's huge. If we didn't keep, we have 93 nuclear reactors running, okay, mostly in the East, because they were sited during the 50s and 60s, where the population centers were really in the East, and they still are in the East.
And so Jim continues, given the president has put aside money, encourage keeping power plants in operation, what kind of support do you think we're going to get in Washington?
Well, this is, nuclear is a funny thing. There's no political constituency for nuclear, right? There's no Texas like for oil. There's no West Virginia like for coal. There's no Pennsylvania like for natural gas. So there's no congressional delegation that is supporting nuclear, because it's not a geographical thing. Okay, nuclear has always been a national thing, right? And since we're not a nation anymore, we're just a bunch of arguing little children states. We can't make a national decision anymore. It's it's like the nuclear waste issue. We know what to do with nuclear waste. It's a piece of cake. I mean, we know exactly what to do with it, exactly how much it's going to cost. It's really easy. We're just not allowed to do it for political reasons. And
yeah. And I read a little bit about this. We have 2 rounds of bidding, and it's an amount of about $6 billion put into the infrastructure bill. And there's 2 rounds of bidding. The first round is only for plants that have announced they're going to close. So if you've announced, like Palisades, that you've announced, yes, we're going to close, then you're eligible to sort of bid on these funds. And I'm sure that, there's more coming, but that was the first condition. And Paula wants us to talk a little bit about rooftop solar. Is that going to solve all of our problems in Washington?
No, it'll help. See, the thing about rooftop solar that's nice is that it doesn't take up any more space. Okay, you already have the structure there. And the nice thing about building rooftop solar in new buildings, new houses, new buildings, is that the cost is almost nothing, because you amortize the cost over the length of the loan period, and you're building a house for $300,000, and the solar panels cost $10,000 or $20,000, and you just put that into the loan, and a homeowner doesn't even feel it. Okay, yet it comes onto the grid, and in that case, it's not a power plant that you have to operate. Okay, it's simply dripping in energy a little bit at a time. So if you do that with all structures, you can have a significant amount of solar, and even if the capacity factor isn't very large here, like it isn't, that's okay, because you're on a rooftop solar. It would be dumb to build a solar array, a huge one in Washington State. That does not make any sense. But rooftop solar is great. Rooftop solar should, be, especially in the Southwest United States, all new construction should have rooftop solar. Now, we don't have enough rare earth elements to do that. Okay, we don't have enough, lithium. We don't have enough cobalt. We don't have enough neodymium. All the things required to build solar, we don't have enough of, and we're dependent on China for 97% of the materials that go into solar. So, this is a problem. Okay, another one of these things that has nothing to do with the technology, but simply with the situation and the global market.
And I'll add, we choose not to build these in Washington State. The Newport, Washington community had a chance to make solar grade silicon there, and they turned it down. So we're simply choosing to build these things in China instead of locally.
Yes, Americans, I'm sorry, Americans are a bunch of children. I hate to say that. They're a bunch. It's like they say they want something, but they do not want to give out anything. Okay,
Mhm.
so the same thing with, they want wind turbines, but they don't want high voltage transmission lines. Well, you can't have it without high voltage transmission lines, especially since wind farms and solar arrays are pretty much out away from the population centers. In order to get the energy to the grid or to those population centers, you're going to have to put in an awful lot of high voltage transmission lines, but they don't like them. All right. Well, okay. What are you going to do? I mean, it's, same kind of thing. Yeah. So the public isn't very good at planning because they don't have a good idea of what is required. And the United States as a whole does not have an energy plan. That's been one of our problems all along. We have no plan as a nation. The states are trying to fill that by having their own little plans, but it's kind of hit or miss.
Yeah. So there's a few more comments got stirred up by that. Matt notes that Avista has a 150 megawatt solar array in Clarkston, and of course that Lila notes solar gets both state and substantial federal subsidies.
Right.
Well, okay. Let's talk about it. What is the plan to tear down the 4 lower Snake River dams and replace that with nuclear? That's about 4.4 gigawatt capacity. Tell us what you thought.
Well, it's a bad idea. I mean, it's just a bad idea. First of all, the plan was to replace them with gas. So now we think it would be good to replace them with nuclear. But that's not in the plan. I mean, that is not in the plan. The plan is to get rid of them and not replace them with anything except wind. And that's not a good idea. Okay, so it'll take about 30 years to decommission them. That's a long time. And if you talk about replacing with nuclear or wind or anything else, that's only the power component, okay, which is a small part of a dam, okay? There's the flood control, there's the irrigation, there's the transportation. There's all sorts of stuff associated with the Snake River dams that have nothing to do with power. So if you focus only on power, then you're going to miss the larger issue. But in terms of power, yeah, if you want to replace it with something, it should be small modular reactors. And that's about the right time frame. If it takes 30 years to decommission these dams, then you've got plenty of time to build small modular reactors.
So related to that are there other dams that are better options? Either maybe the Sammamish or the Upper Snake or the
Skagit? The Skagit River immediately. I mean that's a total waste. And so again, most of the dams, 1,000 dams in the state of Washington, don't have fish passages, don't produce power, and so most of them are for flood control and for irrigation. So, okay, you can deal with the irrigation thing. That's not a big deal. If you want to keep the dams, you need to put in fish passages. We don't have them in most of these dams. That right away would help. I mean, they foolishly didn't do that, when they were built. Okay, so most dams in the state of Washington, except the ones on the Columbia and the Snake, have no fish passages. I mean, a few do, but most of them do not. And so that's where you start. Okay. Now, unfortunately,
that's 20% of Seattle's electricity.
Oh yeah, yeah. I mean, what you mean the Skagit? Yeah. So okay, but the Snake River dams are even more than that. Okay, in terms of the state of Washington. So it's like, hey, wait a second. Is Seattle the only one that counts? Sure. Okay, Seattleites, the only ones that care, and we should.
We got green energy. Figure it out. You figure it out.
I love it. So again, you can power those dams and put in fish passages. Great, just do it. All the dams. So, but again, there's no plan. All anyone does is just talk about the Snake River. It's like, well, why aren't you talking about all the others? I mean, the ones that are, we have never decommissioned a dam as big as any of the Snake River dams. We've never done that. Okay, the ones we've done, like the Elwha and things like that, those are trivial little little dams, okay, and they were hard, okay, and it took 20 years to do those, and they're nothing compared to the Snake River dams. So, this is not a trivial thing. And the big dams, like the Snakes, the sediment wedge that's trapped behind the dam, those are pretty, they're natural, but they're pretty toxic. I mean, there's a lot of lead and mercury and stuff like that associated with them, as well as just small particulates. So if you let those out down, all that sediment downstream, you're going to kill a lot of things. So you can't let that sediment out at more than twice the rate of accumulation, or you're going to have some major problems. Well, that in itself is a major problem. So again, it sounds great. Oh yeah, just decommission the Snake River dams. That's not a just thing. It's a really difficult thing, and we've never done it.
Right. Great. So I'm going to end the stream and let everyone turn on your cameras and microphones, and we'll have a good chat. We can let Dan respond to that commentary as well. But first, let's talk about who we are. We are the Seattle Friends of Fission. You can find us on Facebook and YouTube. Let's start with those two places. Seattle Friends of Fission, and that's FISSION. We have been doing shows once every month, every other month, as well. I do weekly shows on Saturday with the Eco-Modernist Society of North America, and so we're producing content either here with Paula, Lila, and Jim, or myself with Gabe Ignetti, and you'll be able to watch that on the Eco-Modernist channel YouTube. Or on my Twitch, you can catch both programs. Soyaddle, that's Seattle without the C and add in the soy. A little bit of spicy political content there as well, as I try to grow our audience. It's one of our outreach strategies. So thanks everyone. Please connect with us either on Meetup, on YouTube, on Facebook, and even we need to repower our mailing list. Right now, Paula has a list of people, and so if you send us your email in Facebook Messenger or in a Meetup message, we'll be able to have that. Or if you've registered for this, we'll start to collect those and let you folks know when we have more programming. So for everyone on Twitch, I'm going to send you to another education channel called Astro Canuck. He's Canadian, doing live observations of the heavens tonight. So enjoy this educational content.